Classification and Marking Part 2. Recently, the United States government has begun to crack down on spammers. You know, those people that send messages and fill your inbox with all sorts of products that you don't need and probably never even knew existed half the time. Well, what I think they should do is make every single spammer tag their message with a big spam label in the subject line. It just says spam before it. So we could set our email filters that anything that has that in it, we could either immediately delete, never receive, or go to some special junk email folder that we never open. That is a form of marking. And what we're going to look at in this nugget is marking all of our different traffic. In Classification and Marking Part 1, we took a look at how to classify our traffic and segment it into different groups. Now we're going to put a label on it. And the first thing I want to look at is marking really necessary? Is this something that we have to do? I think you'll be surprised at the answer. If we do find that it is necessary, where should I mark? Where's the first place that I should start tagging my packets? And then we'll look at the types of marking. This is going to be by far where we spend most of our time in this nugget, is looking at the different types of markings primarily at layer 3, because this is what our routers look at, and by golly, in our networks, most of the congestion happens right there at the router. We're going to look at two primary ways of marking at layer 3. IP precedence, the old way, and differentiated services code point, the new way. Even the name sounds cool. But before differentiated services enters the picture, you have to even look at the bigger question. Is marking really necessary? Surprisingly, most of the time the answer is no, it's not. Here's why. Every single router, at least the Cisco routers, have the capability of classifying and reclassifying the packets every hop of the way. So if we're sending audio, we can recognize that traffic all the way through and treat it differently. The problem? Well, we have to look in the whole box of the packet. Like we saw in the last nugget, Classification and Marking Part 1, we might have to use a tool like NBAR, which is processor intensive, to look inside the packet and find out what it is. Wouldn't it be easier if we could apply a label right at the first entryway of the router or of the switch that told us what that packet was the whole way through? Just like that spam label would tell us what the email was before we even had to open it. That's why the answer is but. Yes, it really is. It saves yourself a lot of processor cycles on the routers and on the switches that all your traffic is going through. Now let's even look at the bigger picture. You see this internet cloud that has entered the picture. Internet service providers are now providing different classes of traffic for you. Here's what that means. At most internet service providers, they're providing 3 tiers of service that you can sign up for. You have like the bronze tier, the silver tier, and the gold tier. What you're going to do is you're going to tell the service provider, or depending on the service provider, they could tell you what markings will fit in each one of those tiers. For example, you might decide to mark your traffic, your web surfing traffic, with an IP precedence of 0, which is one of the lowest markings that you can get. Goes into the internet cloud with that marking and ends up in the bronze class, which means, you know what, if there's congestion, that web traffic is probably going to get dropped. Meanwhile, your other traffic types like voice over IP or streaming video or Citrix is all going through marked into the silver, or if you pay enough, the gold classes. So the internet service provider will make sure that it gets there from point A to point B unhindered. Those are some of the last traffic types that are dropped. So in that case, yes, absolutely marking is necessary so that we can tell our internet service provider exactly how to treat our different traffic types. So we've determined that it is good to mark your traffic. The next question becomes, then where do you mark it? Well, that concept is what Cisco calls the trust boundary. Simply put, the trust boundary is the first place that you decide to mark your traffic. The reason it got that name is because that marking will be trusted throughout the rest of your network. So if that first device marks it incorrectly, well, you've essentially violated the trust, because the routers may treat that packet either better or worse than it should be treated. Here's Cisco's rule of thumb. Mark the traffic as close to the source as you possibly can. So looking at these three different strategies that we have on the screen, you could look at this top one and say, well, this one is the good strategy. The one below it is better, and the one below it is the best strategy. In that case, we see the IP phone marking its traffic itself. So you might think, well, why don't we always use the best strategy? Well, sometimes our products don't have the capabilities. Some IP phones won't have the capability of marking the traffic themselves. It takes a pretty sophisticated device to be able to insert that information into the header. So if the IP phone can't do it, or the computer, for instance, a computer probably won't be able to tag their traffic, so we come to the next one, the better strategy, where we have maybe a multi-layer switch doing inner VLAN routing. That device might be able to mark the traffic. Or maybe it's just a good old 1900 series switch that doesn't have any special capabilities. Then we move up to the good strategy. The first place that we were able to mark that traffic is at the router. So in that case, it was done. It's just not as close to the source as maybe it possibly could if we got some upgraded equipment. Here's my opinion. Excuse me, as my voice gives out. My opinion is that this strategy right here, most of the time, will do just fine. The reason why is, where does most of your congestion happen? Well, most likely it's going to be as soon as you leave that network onto the wide area network link. So as we travel this way. So if we're able to mark that traffic before it hits the WAN link, then we're pretty good. We're well off because we're now able to manage it over the slow connections. The only time I think that these strategies are good is when you have so much traffic on your network, on the local area network, that you're experiencing congestion even on your trunks, your 1000 or 100 megabit per second links that are going between your switches or maybe from the switch to the router. High bandwidth links at that point would be experiencing congestion, and we might need to implement some sort of congestion management even at the switch level. That brings us to the types of marking. How do we mark our packet? I mean, I visualize when I think of marking, every packet going through the router, and the router has a big box of Crayola crayons that is pulling out different colors and shading the packets. Believe it or not, it's not too far from the truth. It's just not using Crayola or crayons or colors. So what we have is we have these different types of markings that we can apply. Some at layer 2 and some at layer 3. Now layer 2 is typically stripped off at the router hops. And just if you think of the way a packet is processed, that makes sense. As the packets are going through, the router is going to receive them, and the MAC address changes every single hop, or maybe your frame relay DELC changes, or your ATM VPI VCI pair. All of these things, every hop will change. So what that means is all the layer 2 information is removed and then replaced as you go through every single router. Because of that, it's not as popular to market layer 2, but you can do it. The most popular way is by using something known as the class of service field, or QoS field, in Ethernet frames. This is what we use on our Ethernet networks. It's an 8-bit field that allows you to mark your traffic in one of 8 different ways. And we'll look more at this when we get into the hows behind each one of these markings. But as we move down this list, you see that we also have the way to do it in frame relay. Frame relay doesn't have the QoS field. So we are reduced to the DE bit. This means discard eligible. Now if you've played with frame relay for a while, you're used to the service provider marking your traffic as discard eligible. Why would they do that? Well, most of the time it's because you've exceeded your committed information rate, or CIR. And the minute you go above that, all the traffic that goes above is marked discard eligible. It doesn't mean that it's guaranteed to be thrown away, just like if you're eligible to be on The Price is Right, you're not guaranteed to be on there. In this case, it's just if the service provider is experiencing congestion, these packets will be the first to go. The wild thing is now we can mark our traffic as discard eligible. Now you're probably going, why would I ever want to do that? Why would I mark my traffic to be discarded in the frame relay cloud? Well, here's the idea. When push comes to shove, do you want the service provider to be the one marking the traffic that's above the CIR? Meaning they're going to do it at random. You know, whatever packet comes in at whatever time, they're just going to mark it discard eligible. It could be your voice, could be your data, could be anything. Or do you want to be the one that marks the traffic discard eligible if it's going to go above the CIR? My guess is that you would, because that way you have some control. I can say, you know what, I want to send my voice traffic first, and then maybe I have some data, and that will be considered discard eligible because data can recover. That's how we do it in the frame relay world. The ATM CLP bit is essentially the same concept as the DE bit. It's either on or off in the ATM world. And of course, ATM and frame relay are both being replaced by this hot new technology, the multi-protocol label switching, MPLS networks. Nearly every service provider that's out there, every major service provider I should say, has already begun the transition of their internal core networks over to this new MPLS technology. The way that we mark traffic there is using these experimental bits, or EXP bits, which again allow 8 different levels of control through the MPLS cloud. My focus is going to be up at layer 3. The reason why is because these are mainly specific to the technology that they're running on. And to talk about them, you really need to understand in depth each one of those technologies, ATM, MPLS, frame relay. These concepts we all work with every single day. Routers, IP precedence, DSCP, and even QoS. I'll spend some time on class of service because that can be a useful marking that we can use to transition from the local area network to the wide area network. The reason these layer 3 marking mechanisms are so popular is because they survive. Once you mark something at layer 3, it's going to go from point A all the way down to point B. I mean, think of IP addressing. Once you have a source and a destination IP address, those remain in the packet all the way from end to end, with the one exception of NAT. These will remain in the packet from end to end and not need to be modified unless you have a very specific reason to do so. The layer 2, you'll have to remark at every single hop. And if you think about it, doesn't this somewhat defeat our whole purpose of marking in the first place? Saving a few processor cycles so we don't have to constantly do this remarking or rediscovery of what's in the packet? Yes, there is a time and a place for layer 2, for instance, when we're going across one of these ATM or frame relay clouds, but the main thing that we'll be using is layer 3 markings to get the true end-to-end quality of service. And those two ways of marking are IP precedence, as I mentioned, the old way, and differentiated services code point, most often referred to as DSCP. This is the new and more flexible way. Before we get lost in too much theory and design, I want to get our feet grounded in some configuration and show you how to mark the packets that are coming into your router. Imagine that we are this router right here, receiving packets on, say, our fast Ethernet 0 interface. On this router, what I'm going to do is I'm first going to classify the types of traffic that I want to mark. So I'm going to get into global config mode. Let's create a class map, and we'll name it IP phone audio. I have a habit of typing everything in caps that I configure so I can easily recognize it in the show run. So I have right here in class map IP phone audio, I want to match, let's go ahead and use NBAR. We talked about this in the classification and marking part 1. I'm going to match the protocol. Scroll down. Let's use RTP. That is the protocol that we use to stream audio from the IP phones. So I'm going to type in RTP as the protocol that I want to match. And we'll go ahead and exit out of that. So what have we done at this point? Well, actually nothing, because we haven't applied anything. But once we apply it, here's what's going to happen. Traffic will be coming from this phone, make it through the switch, come to the router because maybe it's calling a phone over here, and the router will say, aha, you are RTP packets. You go stand over there. Now, as of yet, we haven't told it what to do with those packets. Remember, class maps just classify. Policy maps is what to do with that packet. Now, we'll eventually start saying, well, you get the priority, you get sent first, you get this much bandwidth and all that. But as of right now, all I want to do is mark it. So I'm going to jump into global config, and I'm going to type in policy map, followed by mark voice. That's the name of my policy map. And I'm going to say for the class, and let's scroll up here, the class name was IP phone audio. Let me copy and paste that down here. So I have class IP phone audio, enter. I'm now under the class for the policy map, and now I need to say, what do you want to do with that packet? In this case, I want to set, this is where we're going to do all of our marking. I'm going to set, and here's all the things I can mark. I can set the class of service, which is a layer 2 marking, and I'll get more into the specifics of these and how to configure and what the different values are. I just want to show you how to mark them. So let's say I want to set, since I'm on the router, I want to set the IP precedence. And then we come to this. What value do you want to give this from a 0 to 7 for the voice that I'm going to be streaming through here? Well, the number one most common and most recommended value to give voice over IP traffic is critical. So we can either type in 5, or I could even type in the word critical. So at that point, I've set the IP precedence to critical. Let me exit out, and I'll just do a do show policy map. Did you know that you could do that? Type do from any configuration mode and do a show command so you don't have to exit back out. If not, there's your tip of the day. So I do a show policy map, and I see policy map mark voice for the class IP phone audio, set IP precedence to 5. But we're not done yet. There's one more thing. Remember, going back to the modular QoS CLI steps, number 1, classify. Number 2, do the policy. What do you want to do? Policy map. And number 3, apply the policy map. We do that to the interface. Now, marking is one of the few things that thankfully can be done on the incoming direction, on the incoming interface. So I'm going to exit out of this policy map and go into interface fast Ethernet 0, which is this interface on the router right here. Now I'm going to type in service policy followed by the name of the policy map. Or actually, hang on, use context-sensitive help, input to say that this is going to be in the inbound direction. Now, whenever you think of these directions, imagine yourself as the router. Hold your arm out. I do this. I look like a goofball, but I do this. I hold my arm out and I say, am I receiving traffic incoming on my arm? If my arm was that fast Ethernet interface, is it coming into me or is it going away from my body, out my arm? That is how I determine what direction. So in this case, it's input. So as packets come into my arm, into this fast Ethernet interface, then we type in the name of the policy map, which was mark voice. I'll place it there. Enter. We now have a policy map that when it sees IP phone audio, or RTP, the real-time protocol, it will mark the IP precedence as 5. That is a complete marking configuration, and we'll get deeper into that. But at this point, we marked it with a 5, but what does that 5 mean? And for that matter, what are all these values that we can mark with? Well, those values differ depending on what kind of marking mechanism that you're using. The most common marking mechanisms, class of service and IP precedence, have 8 values defined, 0 through 7, that you are able to mark your traffic with. Now, what says what you should mark each thing with? Well, that's the beauty of quality of service. You do. You get to go out there and define exactly how you want each packet marked and what value it should have. The problem with that is just because you mark something as being very good doesn't mean that the administrator down the road from you is going to mark something with that same value that's very good. And that means that the administrator down the road from them isn't going to mark it the same way. So what they decided is we need some kind of standard marking system. We're not going to dictate what you have to do, but rather give you recommendations as to what you should do. That's why you see this list right here of the 8 values and what you should assign to either of them. The first thing that I want to start with is 7 and 6. This is class of service or IP precedence value 7 or 6. These are both considered reserved, as in they're so valuable, no traffic that you ever have should ever use them. Now you might think, well, what's more valuable than voice traffic and my voice over IP data? What could be more valuable than that? Well, how about routing protocols or the synchronization protocols of your network? Those can be more valuable because if those can't get to their destination, your whole network goes down. So Cisco and many other providers have said, we will mark routing protocol traffic and things of that nature, pretty much network infrastructure and management traffic, with values of 6 or 7. So no matter what, those will always get there. It's more important for your network to stay up than your voice over IP traffic to get there, because if the network's down, no one's getting anywhere. The first user-defined value that they recommend you use is a class of service or IP precedence of 5. That is where our voice bearer traffic is placed. That's where our voice over IP streamed audio is typically assigned a value of 5. And we'll see that again and again throughout the rest of this course. Video conferencing is right below a 4. You might say, well, isn't video just as important as voice? Well, not if you think about it. If you're seeing a stream video of somebody and that starts breaking up, but you can still hear them, that's typically okay. But if the streaming video is crystal clear, but their audio is cutting in and out and you can't understand it, well, the streaming video is just for looks at that point. It's important, but it's nowhere near as important as the audio. That is typically assigned a value of 4. Now the call signaling is typically given a value of 3, and it's kind of related more towards the voice and video side. This is where it really starts becoming flexible. You can even put some of your very, very important data traffic in 3. But Cisco recommends that you only place, this is known as the RTCP, the real-time control protocol. This is the control protocol, it's real-time transport control protocol. I felt something missing there. This is the control protocol for the voice. And it sounds important, but really it's not as important as it sounds. The primary function of RTCP is to provide the statistics for the call that allows you to check the quality level and how many packets have been sent. For instance, here's a perfect use of it. At any time on a Cisco IP phone, there's a big I button right on it. It's information. And if you're on the phone call, at any time you can hit that I button twice, and it will display all the stats for the phone call. How many packets have been sent, what audio codec it's using, how many have been dropped, the jitter, the delay, pretty much all the stats for the call, and all that comes from RTCP. So if one of those packets are dropped, it of course affects what you can see reporting wise, but it's nowhere near as important as something like the audio itself. Right below the 3 level, this class of service or IP precedence marking of 3, we come into the data. And we hit the 2, 1, and 0 high, medium, and best effort data traffic priorities that we can have. And again, it's totally flexible. It's totally up to you what you want to place in here. But this might be something like good old Citrix. Citrix is a fantastic application. I love it. Metaframe, it's great. However, it is very sensitive to delay and if your packets are dropped. It does not perform well. So that might be a high priority data. Medium might be something like, say SQL replication, or Active Directory, or maybe just important stuff. I'm struggling. I'm thinking of other applications. This really gets down to it. Your mileage may vary. Find the applications on your network that are very important to you, delay and latency and loss-wise. Oh, there's another one up here, SNA traffic, mainframe. And you'll categorize them in your high, medium, and best effort. And best effort really could be, web surfing, peer-to-peer, if you even decide to put that in here. Web, FTP, all of those kinds of things that are just bandwidth hungry but not very important to the business. That's going to be what it looks like when you're tagging these. So getting back to that configuration screen, let me get it right here in the window. When we're looking and we're saying, let me scroll back up, set IP precedence, we have our 7 values. Those 7 are totally customizable by you. And the funny thing is we're just marking it right now. I find this funny because we haven't defined the treatment. We're going to talk about treatments later and saying what traffic has what priority and so on. Truth be told, it doesn't matter what it's marked. If we choose to treat level 5 traffic like dirt, it's going to treat it like dirt. It's totally up to you. Quality of service is very flexible around you. Now, this standard has been around for many years, these 8 levels of marking, and we're going to get into the binary of how these actually tags. It's actually, not in decimal, as nothing in IP can. It's all in binary. But this does not provide the flexibility that we need for our networks today. For example, maybe we have Citrix and SNA traffic, and SNA is slightly more important than Citrix. Well, we can't really define that here. Both of them are going to be tagged with 2, so they're both going to be treated the same throughout the rest of the network. We needed something more flexible. That's where DSCP came about. To understand how these packets are marked using the Differentiated Services Code Point, or DSCP value, we need to get into the nitty-gritty behind the marking. I mean, really, how is a packet marked? We saw with IP precedence and class of service this value from 0 through 7, but where is that placed? Well, if we're using IP precedence, it's placed in the layer 3 header in the type of service field. If we're using the class of service, it's actually part of the layer 2 header. There's a small little 3-bit field called class of service that allows us to tag it with one of 8 values, 0 through 7. But type of service was defined with the original IP standard, and I always remember seeing it and going, what is that used for? And everybody always told me, it's for type of service. Truth be told, nobody really knew because quality of service hadn't really taken hold yet, and this was developed for a future use. I'm sure it was used in niche markets, but quality of service wasn't at the widespread use it is today. So in this type of service field, you have 1 byte of information. And from our IP subnetting, I'm sure we know that 1 byte is 8 bits, zeros and ones. And this is where we can do our subnetting magic and all of that. But really, I'm not going to talk about subnetting. I can hear the sighs of relief already. I'm going to talk about how we mark using the binary. Here's the concept. IP precedence marks with values from 0 through 7. But when you're looking at 1 byte, I mean, how many values can you get, really? Well, this does play a little bit of our subnetting, converting binary to decimal. If we changed all these to ones, and use the powers of 2. We did the 1, 2, 4, 8, 16, 32, 64, 128. Added them all up. What's the value you can get? 255. That's the value maximum that we can use using 1 byte. Then why can we only tag things with 0 through 7 using IP precedence? Well, the reason why is because IP precedence only uses these 3 bits right here. That's right. Even though they have the full 8 bits at their disposal, the standard said, well, we're only going to use 3 because who's going to need more than 8 different levels of service? Well, nowadays we do, but nonetheless, these 3 bits are the only things that are used for IP precedence. So if you changed all those to 1, now remember, these are kind of a segmented 3 bits. These don't exist. This would be a 1, a 2, and a 4. Add all those together. That's 4, 6, 7. So that's how we can get the values 0 through 7 is by only using those 3 bits. It's the same thing with class of service. It only has 3 bits to work with, so it can only use values 0 through 7. DSCP said, you know what? We've got these 8 bits at our disposal, so why not use them? The problem is they didn't use them in the easiest possible method. In the world of routing and switching, you can never just scrap an old standard and start over with a new one, because there's still thousands, if not millions, of devices out there that are on the old standard. That's why we still haven't moved to TCP/IP version 6. Too many devices to upgrade. In this case, we have routers. Let's go ahead and draw a couple routers here. We have routers all over the world that are using the IP precedence standard. So when they came up with DSCP, they said, okay, this will use all 8 bits, but it still has to be backwards compatible with the old standard. So if something is marked with DSCP over here, and a packet is sent this way, and this is an IP precedence only router, it should still be able to understand relatively the importance of the packet. So because of that, they took these 8 bits and divided them into 3 different groups. Here they are. I'm going to go ahead and draw the lines right down here. 1, 2, and 3. I'll go ahead and put 1, 2, 3. These are the different groups of bits that they created for DSCP. This is how I prefer to look at it, and you'll find them written all different ways in all different documentation. I prefer to look at them as the major class. Let me just put major, the minor class, and then we have over here ECN bits. Now the ECN bits I'll talk about a little bit later because they're not really important yet. We'll talk mainly about those when we get to weighted random relay detection. I want to focus in on the major and minor bits because that's really what's used when we tag our packets. DSCP defined many different classes of traffic. As a matter of fact, let me show them to you. I'm going to bring up my router right here, and I want to start off just doing a show policy map. There's my mark voice. Jump into global config. I'm going to get under that policy map, mark voice. It is case sensitive. Class IP phone audio. I'm just getting back under there so I can show you how we mark things using DSCP. I'm going to type in set to set the quality of service values, DSCP, and then, are you ready for this? Poof. We see all these values show up on the screen that we can tag using DSCP. And you look at them and you're, wow, look at all these different things. It looks so flexible. And the very first thing that we have in the list is you can type in a value from 0 to 63 for your differentiated service code point value. Stop right there. I want to talk about why we have 64 0 to 63 different values that we can tag using DSCP. Let's jump back to the whiteboard. I have right here my 8 bits that I can use to mark things. ECN, I just want you to cross out those bits for now. It stands for explicit congestion notification. It's used with a function called weighted random relay detection for a router to say, hey, slow down, you're sending too fast. It pretty much allows a router to be proactive to avoid getting overwhelmed. But that's a totally different function. The actual marking is the function of these 6 bits right here. So if we take 6 bits, 1, 2, 3, 4, 5, 6, and use those to convert to decimal, put our decimal values, 1, 2, 4, 8, 16, 32. Add all those together, and what number do you get? 63. So going back to that window, we have a value from 0 to 63 that we can tag things with. That's right. With IP precedence, we had 0 through 7. DSCP gives us 0s through 63. Truth be told, if you're using all 63 classes that you can with DSCP, you're being way too granular because there's no way you can take 64 different treatments for a network unless you have a very, very large network that has many different classes of traffic going across it that all require different treatments. And Cisco realized that, and the creators of DSCP did too. And they said, you know what? Instead of using all 64 values, 0 through 63, let's define major and minor classes, or what I call major and minor classes of values that we can set. So they took these bits and they split them up into 2 different groups, the major class on the left and the minor class on the right. The first thing I want to focus in is the major class. We have 3 bits to set the major class of traffic, right? And how many values can we get with 3 bits? When we think back, IP precedence used 3 bits. So that's it. 0 through 7 that we can get with our 3 bits. That's going to be the major class of traffic. And that is what allows us to be compatible, backwards compatible with IP precedence. Essentially, we're reducing our functionality and our capabilities of marking down to those 3 bits again. You might be thinking, well, Jeremy, that seems kind of odd. You have this killer new marking system, DSCP, and you're reducing it to the functions of IP precedence. Well, in order to be backwards compatible, we had to. But the beauty is we also have this minor class. So if we do have all DSCP routers, this IP precedence one is gone, and we upgrade to a DSCP compatible router, we now can do kind of sub-marking or minor marking that we can allow to happen so that we are able to say, you know what, here's the major class of 4. But inside of that we have these little sub-minor classes. Let's jump back to the live configuration window because I want to show you something. We have those values 0 through 63, so at any time you could type in a value if you just wanted to use the value, no standard applied. Or we can start using these assured forwarding, or, let me get down here, expedited forwarding classes. Let's jump back to the whiteboard. where do these fit into the picture? Well, if you don't mind, I'm going to clear off a little room on this whiteboard so that I have a little more room to scribble with. Just go ahead and wipe that clean right there. When they defined the DSCP values and the standards for DSCP, they went ahead and defined many different classes that they were able to use. The first one was considered the default class. I'm going to change to a black text there so you can see it. A default class. And that was essentially a DSCP value of 0. And they said, you know what, there's no flexibility in that, that's best effort, no real QoS applied, we're not even going to have a minor class for that. But then what they did was they started defining AF classes. And when you see AF, it stands for Assured Forwarding, meaning there's some sort of QoS on there. They defined AF1, AF2, AF3, AF4, and then finally, they didn't say AF5, they defined EF. That's where we end up with all these different values. Let me just jump back to the screen of the live demo. Scoot up a little bit. Yeah, you see we have AF1, 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 AF2, 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 3, 3, 3, 4, 4, 4. Then we have down here CS. Don't even worry about that yet. But down at the bottom we have default. That's pretty much no QoS applied. And then we have expedited forwarding, EF. That's the ultimate in quality of service that you can apply. So let's talk about this first value first of all. AF1, AF2, AF3, and AF4. This is meant to be backwards compatible with the old IP precedence. AF1 matches up to IP precedence, well, you probably guessed it, IP precedence 1. AF2 matches up to IP precedence 2, 3 to 3, 4 to 4, and EF equals, if you have something marked with EF, they said that is going to equal IP precedence value 5. Of course, the default matches IP precedence 0. Now within AF, they defined minor classes. And again, we had 3 bits, but they said, you know what, we don't even need that much flexibility. They only defined 3 minor classes, and if you ever see it referred to on the Cisco site or any documentation, instead of minor class, they will call that the drop preference. Okay? This is what gets people so mixed up on DSCP, and I have to agree, this is a wildly confusing way to do this. In the major classes, higher is better, right? If you have an IP precedence 1 versus voice IP precedence 5, 5 should win. That's logical. IP precedence 2 versus 3, 3 should win. Higher is better. But when you come to the second value, let me bring this back up, you see that we have AF11, AF12, AF13 right here, AF21, AF22, AF23. In this case, higher is worse. For the drop preference, and this is the good way to think about it, the lower your drop preference, the better you are. So let me grab my text tool again and jump over here. In the AF1 class, we actually have AF11, AF12, and AF13. If you mark something with AF11, it is better than AF13. 13 will be dropped first. The 3 is considered a high drop preference. And if you think of it in terms of drop preference, having a higher number, higher drop preference, that's the way it should work. So if you ever have in your queue an AF13 packet versus an AF11, I almost have this boxing match in my mind. The AF13 packet will lose. The AF11 packet will win because they're both in the same class, IP precedence 1 or AF1, and then it has to rely on the second value to break the tie. Who's going to get dropped? Well, the one with the higher drop preference will. That will be AF13. It does that same thing the whole way down. You have the major class, the major value, the first number, a 1, a 2, a 3, or a 4, and then you have the minor class, 1, 2, or 3. In the minor class, or the drop preference, higher is worse off, lower is better. In the major class, higher is better, lower is worse off. That's why, you know, somebody had too much time on their hands with this one. They went ahead and split the numbers, and that's why I drew this line here between the major and minor class. 2 sets of 3 bits each to tag your traffic with, both with a major IP precedence class and a minor drop preference class. Now, when you come down to default, there is no drop preference. It's kind of scavenger traffic, best effort. Whatever gets there first gets it. First in, first out queuing is what this uses. There is no drop preference. When it comes down to EF, there is no drop preference here as well. You'll never see an EF1, EF2, because they say this should never, ever, ever, ever be dropped. If these are getting dropped, that means you're just out of bandwidth. There's no way that any traffic is getting sent. So they had no drop preferences in here. So when it breaks down, you have 3, 6, 9, 12, 13, 14 different classes of traffic that you can have to categorize with. We've essentially doubled the categories of traffic from our IP precedence by introducing these AF values. Now again, remember, you don't have to use the AF tagging system unless you want to be standards compliant. They defined it this way so that a network administrator can tag their packets and kind of have the general relativity of these markings as they move to somebody else's network that maybe is using a different tagging system. If you just use 0 to 64, it's almost like there's too much flexibility there. Just because I tag my packet with a value of 40 doesn't mean the network administrator down the hall is going to treat those 40 classes better. Or if two companies merge together, it doesn't mean that the company that just merged has a good treatment of 40. They might have defined 50 as a good treatment. So they went ahead and boiled it down, and that's where these AF classes come in. So now, the CS classes, where do these come in? Well, don't worry. This is in no way near as complex as the other one. Essentially, the CS classes come in if you want to use DSCP, but you only want the same flexibility as the IP precedence gives you. You can see right here, CS1 is a value of 001, that's our first 3 bits, IP precedence 1, and they have no drop rating. No drop rating. Essentially, they're not using the flexibility that the AF classes give you. And if you look here, you really get a feel for how these were divided up into their separate classes. I said that we had 3 bits, or two sections of 3 bits, right? 3 here and 3 here. Well, when they defined it, I kind of mushed this one over because this bit will always be a value of 0. They don't use it for the drop preference. So look at this. We have right here AF11 001, right? That's a IP precedence value of 1. Then we have 010. Well, since this is always 0, our counting begins here. This is a 1. You see right here, this is a 2. So we have AF12. These two, if we had 2 plus 1, that would be, and I'm converting to decimal on the fly in my head here, so I just want to make sure I don't lose you. This would be a 3. Then we start over. 1, 2, 3, 1, 2, 3. You see how this works the whole way down? That's what calculates our drop preferences. Then right here you see 1, 1, 1. That's our IP precedence. 2, 2, 2. 3, 3, 3, and then finally 4, 4, 4. When they created EF, they went ahead and defined it like this. That's just always EF. There is no drop preference, but that's the IP precedence value for 5 right there. That's how those markings are set up. So please sit down, let that digest, because that marking system is pretty radical if you compare it to the simplicity of IP precedence. Let me just forewarn you that sometimes documentation and even the certification testing world will refer to the DSCP values differently. Sometimes they'll refer to it by the AF value, and that's all I do. I just say, hey, that's an AF22 packet, or hey, that's a AF43 packet. I only use AF values because decimal, I mean, who cares about what the decimal number is? However, sometimes documentation will refer to it that way. So here's what they mean. If you see an AF value of AF23, let me remember that, 010110. Come over here, 010110. That's the binary representation of AF23. Okay? Now, there is also a decimal representation of AF23. So, let's convert this over to decimal. 1, 2, 4, 8, 16, 32. We have a 2, we have a 4, that's 6. Plus 8, that's 14, right? So AF23 really equals a decimal value of 14. So if you went in here and typed in 14, it would assume, I mean, essentially that's the equivalent of AF23. So sometimes you'll see documentation say, I'm marking the packet AF23. That's good documentation. Sometimes you'll see documentation saying, I'm using DSCP value 14. That's bad documentation. And sometimes you may even see a certification test say, I have a DSCP value marked 14. What AF is this? So you're going to have to figure it out, do the binary, and figure out the different pieces and divide it up. So I just wanted to forewarn you that you may see these things referred to differently because of how DSCP gives you that ultimate flexibility to tag things. If you're feeling a bit overwhelmed by DSCP right now, don't worry, that's normal. It's a radically different way of marking our traffic compared to the simplicity of IP precedence. Please go back 10 minutes ago when we started explaining how DSCP was marked and go through it again. You'll get it. It's just having to figure out how those 8 bits are divided up is it's a totally different way of looking at things. But once you get it, you'll get it, and it'll sink in and stay with you forever. So in this nugget, we saw, first off, the question, is marking really necessary? The answer is no, but yes, in most modern networks. You don't have to mark, but you really need to when you're integrating with service providers or moving traffic over to different parts of the network that maybe don't have the processor power to reclassify every single hop. We then saw, where should we mark? That was as close to the source as possible. That trust boundary should stretch as far as our equipment will allow us to, because the sooner you mark, the sooner you'll be able to say how those packets are treated all the way across the network. Then we spent most of our time in the types of marking, looking at layer 2 primarily with the class of service, which a switch, a highly functional switch, would be able to understand. We also saw some of the, I want to say proprietary, but it's mainly different network types, like frame relay using the discard eligible bit, ATM using the CLP bit, MPLS using the experimental bits, all these different types of networks and their way of marking at layer 2. But we also have to remember every hop removes the layer 2 information, so we really want to stay with layer 3, and we saw our IP precedence using the 7 values of marking and DSCP using up to 64 different values of marking to classify our traffic. I hope this nugget has been informative for you, and I'd like to thank you for viewing.